Welcome back to The Explainer. I am so incredibly excited to take you on this journey today. We're looking at one of the most brilliant, audacious, and frankly, risky leaps of intuition in the history of science. We're going to explore how one man dared to map the architecture of matter itself. He quite literally played a giant game of chemical solitaire with the building blocks of the universe to do it. This isn't just a story about chemistry, it's a story about trusting your gut against the prevailing wisdom of the time. Imagine you've got this massive jigsaw puzzle, right? But the box doesn't have a picture on it, and to make matters even worse, half the pieces are completely missing. That is exactly the situation early 19th century scientists found themselves in. They knew of about 50 distinct chemical elements, but they had absolutely no idea how many more were out there or how they all fit together. So how do you organize the building blocks of the universe when half of them haven't even been discovered yet?
Section 1. The Chemistry Puzzle, Organizing the Unknown.
To truly appreciate this puzzle, we actually have to forget what we know today. Forget protons, neutrons, electrons. Scientists back then were completely in the dark about all of that. They had to organize the unknown using only what they could observe and measure right there on the surface. And they were caught in this massive scientific tug of war. On one side, you had relative atomic mass, basically just how heavy an element is. On the other side, chemical and physical properties, how the element actually behaves in the real world. Like, does it react violently with water? Is it a gas? The huge problem was, if scientists strictly followed a simple list from lightest to heaviest atomic mass, elements ended up sitting next to other elements they had absolutely zero in common with. The chemical families were totally wrong. It was, quite literally, organized chaos.
Section 2. Mendeleev's Brilliant Gamble, Breaking the Rules in 1869. This is where Dmitri Mendeleev enters the picture. He decided that the existing systems weren't just a little flawed, they were fundamentally missing the grand design. His approach was so radical that a lot of his peers thought he was being wildly speculative, maybe even unscientific. What we're looking at here is the front page of the very first edition of Mendeleev's textbook, The Principles of Chemistry, published in Russia in 1869. Now, this wasn't just some standard educational manual. It was the absolute vehicle for his revolutionary framework. While writing this exact book, it clicked for him. He realized he could actually blend both atomic mass and chemical properties to create one cohesive periodic table.
So the really crucial point is how he actually pulled this off. He took three major, highly calculated risks. First, he just left blank gaps. Where other scientists tried to awkwardly cram known elements together to make them fit, Mendeleev essentially threw his hands up and said, "We are missing something here, so I am leaving it empty." Second, he actually went ahead and predicted the atomic mass and properties of those missing elements. He was essentially predicting the future. And third, when his system demanded it, he intentionally broke the strict rule of ordering purely by increasing atomic mass. He decided to trust his own chemical intuition over the rigid numerical rules of his day.
The absolutely perfect example of that third risk is the relationship between tellurium and iodine. Tellurium has a heavier relative atomic mass than iodine, so if you're following the strict math rule, iodine must come first. But Mendeleev looked at them and said, no way. Iodine behaves like fluorine and chlorine. Tellurium behaves like oxygen and sulfur. So you know what he did? He simply swapped them. He put the lighter one after the heavier one just so they would align perfectly with their chemical families. His peers thought this was total madness. I mean, how can you just ignore the math?
Section 3. Science proves him right. The vindication of intuition.
Decades passed. Mendeleev's table was definitely useful, but it was still highly controversial. It wasn't until the early 20th century, as laboratories finally began to unlock the secrets inside the atom, that the world realized just how much of a visionary this guy was. The discovery that completely vindicated him? The isotope. Isotopes, if you need a quick refresher, are just different forms of the exact same element that have the same number of protons but different relative atomic masses. Think carbon-12 versus carbon-13. Because an element can actually have heavier or lighter versions of itself, ordering the periodic table purely by average atomic mass is inherently flawed. So the discovery of the isotopes perfectly proved why Mendeleev's decision to swap tellurium and iodine based on their properties was 100% correct. He had no idea what an isotope was, but his intuition for the architecture of matter was just incredibly spot on.
Section 4. Europe reacts to Mendeleev, the ripple effect.
So how did the scientific world actually adapt to this earth-shattering realization? Well, it definitely didn't happen overnight. The spread of Mendeleev's table is this fascinating study in how education and academic infrastructure actually govern the speed of scientific progress. Russia, naturally, adopted it immediately in 1869 with his textbook. Because Germany and the Czech lands had deeply established university systems and really quick translations of scientific journals, they integrated the table into their textbooks by the late 1870s. Serbia followed soon after in 1880. But there was a really notable delay elsewhere. Croatia, for example, didn't have a textbook featuring the periodic table until 1901. Why the massive 30-year gap? Well, at the time of Mendeleev's publication, Croatia simply didn't have a university chemistry program yet.
Section 5. Croatia's unlikely early tribute, a Slavic recognition.
Now, despite that massive delay in their educational system, a truly remarkable piece of scientific history happened right here at the Yugoslav Academy of Sciences and Arts in Zagreb. It proves that you don't actually need a massive university infrastructure to recognize pure genius. In 1882, this institution did something completely unprecedented. Even though their high schools were still using old German chemistry textbooks that didn't even mention the periodic table, the naturalists in this building became the very first scientific academy in all of Europe to elect Mendeleev as an honorary member. In the exact same year that the highly prestigious Royal Society in London gave him the Davy Medal, this academy in Zagreb recognized his world-shifting contribution. Check out these incredible artifacts. On the left, we've got the handwritten justification by Croatian geologist Đuro Pilar. It's a meticulous list of 43 of Mendeleev's scientific papers, really proving that they were closely tracking his genius from afar. And on the right, that's Mendeleev's personal response in 1883. He thanked the Academy for the honor, and he noted that it encouraged him to continue fighting for the, quote, Slavic idea. Historical context tells us that at this time, recognizing a prominent Russian scientist was partly a symbol of resistance against the cultural pressures of the Austro-Hungarian Empire. It just goes to show how science and cultural identity were deeply, deeply intertwined.
But the reality of education still lagged way behind those high honors. Despite the Academy's profound recognition in 1882, it took nearly 2 decades for this knowledge to actually reach the students. Finally, in 1901, Julij Domac published this textbook, An organska chemia. It was the very first Croatian textbook to contain a dedicated chapter on the periodic table, which finally allowed students to systematically learn what the Academy had been celebrating for 19 years.
Section 6. The backbone of chemistry, from speculation to fundamental law.
We've seen how Mendeleev's creations survived that initial wave of skepticism, adapted to huge new discoveries like isotopes, and slowly permeated the educational borders of Europe. And as it became standard curriculum, the visual representation evolved too. By the time Gustav Janicek published this 1919 university textbook in Croatia, you can clearly see the short-form periods, the inclusion of the newly discovered noble gases like helium and neon over on the left, and yes, those famous blank spaces that were still patiently waiting for the march of scientific discovery to fill them in. It wasn't just a chart, it was a living document. What started as a massive, speculative leap by a guy who simply refused to follow the strict atomic mass rules of his peers ultimately became the universal language of science. The quote here says it all. His predicted elements were discovered, confirming the table's power. It's now the backbone of chemistry. Those elements he left blank gaps for, things like gallium and germanium, were eventually discovered, and they matched his predicted properties absolutely perfectly. It is the ultimate scientific vindication.
Mendeleev looked at the known world and realized the picture was incomplete. He had the courage to literally leave blank spaces for the unknown. So it really makes you wonder, what undiscovered gaps might still exist in our understanding of the universe today? What established, rigid rules do we currently follow that some future visionary is going to need to break to reveal the next layer of reality? Just think about that for a second. Keep learning, keep questioning, and I really hope this explainer has sparked a much deeper appreciation for the magnificent architecture of matter. Catch you next time.